So let me first ask the people that are remote to remember to mute their mics so we don't get interference during the seminar. So today I'd like to welcome Steve Kahn from Standford University and SLAC. So Steve is going to talk to us about the LSST survey design and some of the exciting science topics. So Steve, if you're ready, I leave it to you.
Okay, thanks, Nicola. So let me thank you in general and the community for inviting me to this webinar about LSST. I think many of you are aware we've been in discussion with the Brazilian community about a Brazilian involvement in LSST for quite some time now. And in fact, we had a symposium in Brazil, I think it's 3 years ago now, where we had at least some sampling of the community. So for those of you who were there and maybe are more familiar with this topic, I apologize in advance, but what I've decided to do for a larger audience is to give a general overview of what LSST is and what its design looks like, and then I'll make some brief comments about a range of different science topics, just to give you a flavor of what we hope to achieve with LSST. So first off, what is LSST for those of you who are new to the project? In a nutshell, it's an integrated survey system which will conduct a decade-long, deep, wide, fast time domain survey of essentially the entire southern sky. We utilize an 8-meter class telescope with a very broad field and coupled to a very large imaging camera. In fact, it will be the largest electronic camera ever assembled when we complete it. And then a very extensive data processing system which is designed to accommodate the very large data volume that LSST will produce. So over the decade of operations, we'll acquire, process, and make available a collection of something like 5 million distinct images. And then, of course, we'll do the detection of objects in those images and produce catalogs. Those catalogs will include more than 37 billion distinct objects and something like 7 trillion sources, where a source is defined as an object that was there at some particular time. And then because we'll make many repeat exposures of every part of the sky, we'll develop a census of what we call time domain events, which are things that have changed in the sky, either because an object has changed in brightness or because it's moved. And there'll be tens of billions of time domain events during the course of the 10 years. We'll produce something like 10 million per night. So this is not going to be simple target of opportunity type follow-up science where we give you a limited number of things to look at. The real question of how to use that time domain survey is, how do you filter it down to find the really rare and interesting objects that you desire. So as you can well imagine, with a database like this, a very broad range of scientific investigations can be enabled. And they all utilize a common database and alert stream. We call that sort of massively parallel astrophysics, one database that serves lots of different science investigations. And those range from searches for small moving bodies in the solar system to precision astrometry of the outer regions of the galaxy to monitoring of transient phenomena in the optical sky. And then, as you'll see, part of this project is supported by the Department of Energy, the Office of Energy Physics, and the reason for that is that LSST will also provide crucial constraints on our understanding of the nature of dark energy and dark matter. So this next chart is a summary of the high-level requirements of LSST. The main survey area will be a minimum of 18,000 square degrees. Our current simulations are showing that we'll cover something more like 20,000 square degrees, but this is our requirement, that at least 18,000. Each piece of that sky, each object in that sky will be visited a minimum of 825 times over the 10 years. And a visit, is a pair of two 15-second exposures separated by a 4-second interval where we open and close the shutter and read out the entire 3 billion pixel array. So we'll do this survey in 6 distinct colors, U, G, R, I, Z, Y, which go from 320 nanometers out to beyond 1 micron. The next line down is the limiting magnitudes for each of those colors, and you can see we go extremely faint, of order 24 to 20, close to 25th magnitude in a single visit, a pair of 15-second exposures, and somewhat shallower in the other extreme bands. So these are very deep images on each visit, and then of course with the 800 to 1,000 or so visits that we'll get over the 10 years, we'll produce in the end very, very deep images of the entire southern sky. A lot of the science that we hope to do with LSST depends sensitively on our calibration, in particular the photometric calibration. And so we've adopted tough requirements on that. 2% absolute photometry and better than 0.5% repeatability for the time domain survey and the comparison of different colors for things like deriving photometric redshifts. LSST will be placed at a very good site where the median delivered seeing is about 0.6 arc seconds, and we have a requirement that the total image quality per exposure has a median of about 0.7 arc seconds. So we control the instrumental contributions to the image quality to a high level. I mentioned this very large number of time domain events, 10 million a night, and we have a requirement that we broadcast those to the world with a latency of less than 60 seconds. So within 60 seconds of having determined that an object has changed in brightness or moved in the sky, we will broadcast that to the world. And as I said, the big challenge then is going to be how do you use all those alerts in a productive way. And of course that's a science-dependent issue. So we as a project are not telling the community which events are especially interesting. We hope to engage the community in helping us to determine that, and they can filter on those alerts to find the objects they really want to follow up. And then we will reprocess the data annually, all of the data each year. The total LSST database we will reprocess each year and make available to the partners in the project. So we tried to capture an idea of this very broad range of science several years ago, near the end of 2009, when we compiled something we called the LSST Science Book. This volume consists of something like 650 pages, and there were 250 distinct authors that contributed text to it. And this list on the left-hand side are the chapter titles, just to give you an idea of the range of science we do. So after some initial introductory chapters, you can see each of these chapters is a very distinct area of science: the solar system, stellar populations, the Milky Way, etc. And we don't have a single chapter called dark energy or dark matter because, in fact, given the broad range of analyses one can do, there are actually 5 distinct chapters that bear on the questions of dark energy, and those are listed there. So where is this project? This is the current integrated project schedule. So we are right here, and in fact you can see that's kind of a crucial time in the project because it's the indication of the formal start of the construction phase. LSST is a collaboration, involves a collaboration between the National Science Foundation and the Department of Energy in the United States. We were in the approved budget that came from Congress to begin construction this year, starting July 1st. And we've just had the approval of the National Science Board to do that. So we will formally begin construction this coming July, and that will carry through. And of course, we've been working on the project for a long time before this. And so the design is very mature. And in fact, the formal beginning of construction means we actually award the contracts to a number of vendors that have already been selected to cut metal and prepare the site. So with this development phase, you can see a whole bunch of intermediate milestones now that lead to the final system. We formally will start the 10-year survey as projected near the end of calendar 22, something like October of 22. But there'll be a lot of data that will come earlier while we're in the commissioning period. In particular, we will first mount a commissioning camera, which is representative of the full camera, on the completed telescope as early as mid-2019 and start to acquire images. And then we'll have the full camera on the telescope early in 2020. And so there'll be a lot of data and science, and science coming out even before we formally start the 10-year survey itself. So a few slides about what LSST looks like. First off, we'll be sited on a mountain called Cerro Pachon, which is in central Chile. This is a well-developed astronomical site. It already is sited there is already the Gemini South telescope, which is an 8-meter telescope, and the SOAR telescope, which is Brazilian involvement, is a 4-meter telescope. And it's only 5 kilometers or so from CTIO, the Cerro Tololo Inter-American Observatory. The nearest city where the base facility will be is La Serena, which is a coastal town in Chile. And so LSST will have a major facility in La Serena and, of course, the summit facility on Cerro Pachon. And as many of you probably are aware, this site is actually owned by AURA, the Associated Universities for Research in Astronomy, which is the prime contractor for the NSF role for LSST in the States. So this is what the dome and summit facility will look like. It's a somewhat unusual design, which takes account of the prevailing winds in this on this mountaintop. In particular, the prevailing winds kind of move in this direction over the peak, and so a lot of the energy dissipation from the building occurs downstream of those winds and won't affect the dome seeing. As you can see, the dome design is also a highly louvered design to try to equilibrate the air temperature in the vicinity of the telescope, again to reduce dome seeing. We've actually already leveled this site, so the picture you see at the bottom here is what it looks like today. We, in fact, are just about to announce the selection of the site facility vendor, which is a Chilean company, and they will begin construction this summer. So let me make a few comments about the optical design for LSST, which is also somewhat unusual, and this flows directly from the science requirements. So the overall logic is kind of summarized here. The median delivered seeing at the site is 0.6 arc seconds, as I mentioned earlier, and with the usual sort of 3 times over sampling, that would give you a plate scale of about 0.2 arc seconds per pixel. Now, it's pretty obvious with such a large field of view that we require for this facility that it's going to result in a very large camera, and that's going to be the governing technical constraint. So to keep the camera size as small as possible, we want to obviously have the pixel size as small as possible. But there's a minimum pixel size that you can incorporate, not only for technological reasons, but for science reasons. Due to, we are using deeply depleted CCDs in order to get the broad color coverage. And you need to worry about charge diffusion in those devices. And so if you make the pixels much smaller, about 10 microns, then you're not accomplishing much because the charge distribution will spread over the pixels. And you'll also limit the full well capacity. So the minimum pixel size is about 10 microns. If we make that correspond to 0.2 arc seconds, that gives us the plate scale, which in turn determines the focal length, which is 10.3 meters. Then you take the single visit depth requirements that I showed you earlier, and you can calculate how large an aperture do I need in order to collect enough light in 15 seconds to reach those depths. And the minimum aperture diameter is about 6.5 meters, which tells you that the focal ratio of the system has to be less than 1.5. So it has to be a very fast optical system in order to come close to meeting those requirements. Then you take the number of required visits that I indicated, each visit corresponding to 30 plus the interval time, something like 39 seconds per visit. And you say we want to get all those visits over 18,000 square degrees in 10 years. How large a field of view do we need for each visit? And you come up with a number of 3.5 degrees, which given 0.2 arc seconds per pixel tells you need a very big camera, 3 billion pixels, as we had already indicated. And with that plate scale, the focal plane of that camera is physically very large. It's 63 centimeters. So these give you sort of the main parameters what telescope and camera look like, and you can see they really just come from those science requirements. There weren't a lot of design specificity that go into these numbers. And then finally, there's a requirement on the telescope mount design, because we want to do a new set of 2 exposures every 39 seconds or so, and we don't want to spend a lot of time waiting for the telescope to slew and settle. So we need a telescope mount that is as compact and stiff as possible, so we can do so many exposures a night at high efficiency. So this is the optical design. We call it a modified Paul Baker design. As you can see, it consists of 3 primary reflections. So the light comes in collimated off the primary mirror, which is an aperture, which is an annulus, as you can see, and then is reflected off a convex secondary and on into a tertiary before it's focused in the camera, and there are 3 refractive lenses in the camera plus the filters. So this 3 bounce design is actually endemic to all wide field telescopes, and it comes largely from the requirement that you need to cancel both chromatic aberrations and astigmatism in order to get the decent image quality over a very large field. In fact, if we were using film for the camera, if we weren't using electronic detectors which need to be cooled and housed in a vacuum cryostat, then in fact the 3 bounces alone could provide the desired image quality over the whole field. But because our focal plane is inside a cryostat, which needs an entrance window, then there are chromatic aberrations that would be introduced by that entrance window. In order to cancel those aberrations, we need these additional refractive optics in the camera. And you can see these are thin, high aspect ratio optics. They don't have a lot of optical power. The main thing they're doing is taking out that residual chromatic aberration that you would get from the entrance window alone. And L3 is actually the entrance window of the cryostat, and that is a lens. That's the final element of the optical system, and the focal plane sits right behind it. So in fact, we've made quite a bit of progress on the primary tertiary mirror. You could sort of gauge from the optical design that what we chose to make these 2 surfaces nearly coplanar, or at least close to each other, which means they could be fabricated out of a single monolithic substrate. We're using the borosilicate technology, which has been under development for a number of years at the mirror laboratory at the University of Arizona. And in fact, we started this mirror roughly 4 to 5 years ago using private money, and it's almost complete. It will be finished actually in July. So in this picture, which comes from the mirror laboratory, you can see the primary surface as an annulus, and then the break-in figure, which as you go into the tertiary. And so this is very, very close to complete. At the time we started it, it was the critical path. We were expecting to get the federal money on a somewhat sooner time scale than it showed up. And so we were thinking that at that stage that we would have this mirror just in time to start using it, incorporating it into telescope mount. But given the funding delay, we actually will have this mirror in storage now for 2 years. So this is a figure of the telescope mount. As you can see, it's this very stiff, compact design. I mentioned it points to new positions in the sky every 39 seconds, and typically those new positions are roughly 1 field away. So it'll slew and settle roughly the 3.5 degree distance between fields on a time scale of order 4 seconds. The camera is also a very challenging instrument to design. So these are some issues that we face in trying to design the camera. We need a very large field of view. And of course, as you've seen, that implies a physically large focal plane with small pixels. Of course, the only way to do that is to mosaic a large number of sensors with narrow intergap chips and interchip gaps. And in fact, our design incorporates 189 distinct 4K by 4K CCDs with roughly 100 micron gap between each of those sensors. It's a very fast beam, as I mentioned. With the current design, the beam is actually f1.2, and that implies a short depth of focus, which means we have tight alignment and flatness tolerances. roughly 10 microns peak to valley over the entire sensor array. The camera, as you saw, is located in the telescope beam, so there are tight constraints on its envelope, mass, and dissipation of heat to ambient to avoid screwing up the images by having convective eddies in the vicinity in the optical beam. We're aiming for very broad spectral coverage, as I mentioned, 300 nanometers out to a micron or so. That requires deep, fully depleted CCDs, but with minimal charge spreading. In order to have high observing efficiency, we need to read out this camera very fast. We are planning to read out the 3 billion pixels in 2 seconds. If you try to read out CCDs at a very high rate, you increase the noise. So the only way to beat that down is to parallelize the entire system. And the sensors are highly segmented. There are 16 readout ports per sensor. And as I mentioned, there are 189 sensors in the focal plane. So that's a few thousand channels of electronics. And the very large number of signal lines that would require has motivated us to actually incorporate the electronics directly in the cryostat. And I'll show you that in a minute. So this is what the camera looks like. For comparison, there's a stick figure here. Our project manager for LSST is Nadine Kurita, and when she joined the project, she changed all the male stick figures to female stick figures. She also pointed out she's about 5 feet 5 inches tall, or 1.65 meters tall, which is exactly the diameter of the entrance lens of the camera. So you see how large an instrument this is. It's about 3,000 kilograms. It's roughly 3 meters or so from front to back. Lots of internal components in the utility systems. This is the cryostat. There are filters you can see here which are on a carousel to insert into the field, and the refractive optics in the front. So this is what the focal plane looks like. Each of these blue squares that you see is a 4K by 4K CCD, and we group 3 by 3 of them, or 9 sensors together in what we call a raft, which is the red square. And then the focal plane is assembled by integrating those 21 distinct rafts into a coherent structure. So each of these rafts is a 12K by 12K camera of its own, and all of the readout electronics through digitization, et cetera, are incorporated in the footprint of that raft itself. So the output of each one of these red squares is a single optical fiber carrying the data away. And the design, that modularity in the design is very helpful for integration and also for maintenance. If we lose a CCD or multiple CCDs, we need to replace them. We can do that by removing one of these rafts without disturbing the others. And that's crucial for trying to design an instrument that will last for 10 years. At the corners of the focal plane, you can see there are what we call corner rafts, which contain wavefront sensors and guide sensors. The wavefront sensing scheme is curvature sensing, which uses simultaneous intrafocal and extrafocal images to deconvolve what the wavefront errors are. And we have active control of all 3 mirrors of the system, the primary, the tertiary, but also the secondary, to deal with those wavefront corrections. So another big challenge for LSST has to do with handling all of these data. LSST will generate something like 20 to 30 terabytes of data per night. The first issue is how do we get that data out of Chile and into our processing system. This is the architecture of how we will do the data handling. There is, of course, a summit facility at the telescope which acquires the data and stores it, and then a major processing facility in La Serena where we will do the crosstalk correction, long-term data storage, and there will be a full data access center there for use by the Chilean community and also by the other partners if they need it. Then we have these long-haul networks. These are essentially 10 gigabyte links. Bring the data to our primary archive facility, which will be at Urbana-Champaign at the National Center for Supercomputing Applications. And there we will do the alert production, the data release production, calibration, et cetera. And there'll be another data access center there for the use by the U.S. community. And the headquarters for LSST will be based in Tucson. So there are two redundant paths to get the data into the U.S., so it's a fairly robust system in the case of network outages. The ultimate LSST deliverable, of course, are these reduced data products. That will require a petascale supercomputing system at the LSST archive in Illinois, where it will process the raw data, generating reduced image products, time domain alerts, and catalogs. And I think those of you at Linnea are familiar with the sorts of analyses that are done, a set of image processing routines, detections of objects, etc. The data access centers in both the U.S. and in Chile and in other countries that join with us on this project will provide end-user analyses by querying the databases. The data volume is so large for LSST that the primary method of analysis will be to send scripts for processing to the data centers, running those scripts on the catalogs that are in the center, and then delivering the scientific results back to the user, just given the I/O complexity of accessing such a large data volume. So from a user's perspective, this is what LSST will provide: a stream of 10 million time domain events per night, detected and transmitted to event distribution networks within 60 seconds of observation. One of the things that will come from that will be the moving bodies in the solar system, which are about 6 million, where we'll have orbits for. We call that level 1 processing. Then the level 2 processing is the derivation of these catalogs, fully calibrated catalogs. We're expecting the catalog eventually to contain about 37 billion objects, 20 billion galaxies, and 17 billion stars, and about 7 trillion observations for sources, and maybe 30 trillion measurements, because we will also do some force sources where we take the position of an object, which is known to vary in the past, and derive upper limits if it's no longer detectable. And then finally, we'll also produce these deep co-added images over the 10 years, which will get down to about 27 times. This is where the project stops, below level 2. But of course, to do science with these data is going to require other additional software to conduct specific science analyses. We call that level 3, and the requirement on the project is that we enable the production of level 3 software by the community at large by having various user-specified custom processing and analysis. If you're curious about the computing requirements, these charts are a few years old, but they show roughly where we were projecting. So at that point, we were thinking of starting the survey. This is based on an earlier funding model, something like 2016 or so. And you can see the linear ramp up as the data volume starts to increase. On the right is, some of you may be familiar with these top 500 charts, where the top line is the fastest computer in the world, and the bottom is the 500th, and the middle one is the 250th. And so you're seeing Moore's Law here. When LSST comes online, we'll be roughly there. So we'll still be an impressive computer center, but nowhere near pushing the requirements of the fastest facilities. Okay, so that's a quick introduction to the system. Let me now turn to just an overview of some of the science that we hope to do with LSST. So starting with the solar system, as I mentioned, we'll detect and determine orbits for millions of small bodies in the solar system. The various classes of these kinds of objects, near-Earth asteroids, which could, and the subclass potentially hazardous asteroids, which could potentially impact the Earth. Main belt asteroids, Trojans, which are objects which have resonance with planets, trans-Neptunian objects, Kuiper belt objects, Jupiter family comets, etc. So understanding the origin and behavior of these various systems is crucial for modeling the formation and evolution of the solar system, and telling us how we got to where we are today. This is a plot, very interesting plot taken from Sloan data, which shows for the asteroid families the distribution and the sign of the inclination of the orbit as a function of the semi-major axis. And the different colored points on this plot are meaningful. So these are false colors, but still the different colors correspond to objects which have a characteristically different spectrum or different albedo as observed. Now, one of the interesting things is for each of these points, you can construct its orbit. So you can also work that orbit back in time. And when you do that, even with Sloan data, what you find is that the various blue points actually coalesce at a much earlier epoch in the history of the solar system. Same for the green, pink, and orange points, etc. So what it's telling you is that all of these various small bodies were largely produced by fractionation due to impacts. And so tracing back in time that distribution tells you literally the evolution of the solar system. So in that sense, LSST is kind of a time machine that allows us to trace back the history. And we'll see that repeatedly for other astronomical topics. So this has already been done with Sloan, and we'll do this, of course, something like 100 to 1,000 times, with a 100 to 1,000 times larger sample of LSST. Turning to stellar physics and stellar populations, LSST will individually resolve and detect billions of stars in the Milky Way and the neighboring group of galaxies. And of course, studies of such large samples can address a multitude of astrophysical issues associated with star formation evolution, the assembly of the Milky Way galaxy, and the origin of the chemical elements. And so key techniques for those investigations, most of these are classical astronomical techniques, the construction of color magnitude diagrams, derivation of trigonometric parallaxes to establish absolute distances, stellar proper motions to separate associations from background stars, and then, of course, the intrinsic variables using R.R. Leary and other variables of standard candles, and using eclipsing binaries to measure stellar masses. So these are color magnitude diagrams of star clusters. Most of you are familiar with this. And, of course, LSST will do this in spades. What's really new, though, is that we'll have parallax measurements and at least proper motion measurements nearly to the edge of the galaxy. So we'll be able to, in contrast to what's been done before, we'll actually be able to put an absolute magnitude calibration on all these. And that will give us very high precision tests of stellar structure and evolutionary models. So this next chart shows you the sort of numbers we're projecting as a function of magnitude. These are the errors that we expect on the parallax and proper motion. And you can see that they're at the sort of milliarc second level, which means that we'll be able to use these techniques to determine distances out to a kiloparsec or so, which at high latitude essentially takes us out of the galaxy. So that's what's really new with LSST. And there are lots of interesting things you can learn about the Milky Way from the stellar populations if you can do those cuts. So, for example, if you make cuts in the color magnitude diagram and in proper motion, you can separate out all the field stars. Again, this is Sloan data where this was piloted, and you start to see structure in the sky which correspond to tidal streams of smaller satellite objects to the Milky Way that over the course of cosmic time fell into the potential of the Milky Way, and then a sort of tidal effect strip out stars from those satellite galaxies and leave these trails. And the trails are interesting not only because they tell us the evolution of the Milky Way, how the Milky Way accreted its surrounding smaller objects, but these tidal trails are actually orbits in the dark matter potential of the Milky Way. And so they can be used to trace out the dark matter distribution. So there's a lot of potential there. In terms of getting precision mass estimates for testing stellar evolution models, one of the primary techniques will be to use eclipsing binaries. So this plot shows the probability of us detecting and measuring the period of an eclipsing binary as a function of its period. You can see that where log p of 1 corresponds to 1 day. For the short period variables, we essentially will detect them with very high probability. And of course, that starts to fall off as you get timescales more to a year or so, just because we don't have so many cycles. But we'll get an enormous population of eclipsing binaries, and we'll have enough data in order to do the mass determination for each of these. So a very rich data set there as well. One of the most exciting areas of discovery space for LSST will involve transients and variable stars. And LSST's time sampling, which is really unique among major large-scale facilities, will allow the detection of stellar variability on timescales from seconds to years. And there's, of course, a wide range of phenomena that can be studied with such a rich data set, explosive events like supernovae, novae, gamma ray bursts, etc., periodic variability associated with binarity, as I just showed you with eclipsing binaries, intrinsic stellar variables like Cepheids, Lyrian mirrors, etc., which are important for distance measurements, geometrical effects such as gravitational microlensing, and of course the dimming of stars as they're occulted by transiting planets. So this is a plot, an earlier version of a plot actually taken from Sri Kulkarni, which is kind of an indication of where transients sit on the time domain plane. So the vertical axis here is absolute magnitude, how bright they are. The horizontal axis is a characteristic time scale of variability. And so you can see, sort of well-known classes of explosive objects like type 1a supernovae or classical novae sit in particular places there. Core collapse supernovae are distributed a little bit more distinctly. These are luminous blue variables. The interesting thing about this plot is not where individual objects fall, but just how much of it is open. And a lot of it is open not because there are no objects that vary at those magnitudes and on those timescales. It's because we've never really had a facility to look. So there's a lot of discovery space here to find new classes of transient objects, and then, of course, to try to figure out what they are. So we've done detailed simulations to get a rough idea of what the content of the transient variability samples, and that's shown on these pie charts. So on the left, we're showing the total population, and actually what you find is 75% of the transients we'll see actually correspond to asteroids that have previously not yet been cataloged. Another 20% will correspond to known asteroids. 4% will correspond to stellar variables of the types we're familiar with, and only a tiny sliver actually will correspond to transients. But if you blow up that sliver, the 1%, and look at its contribution, roughly half of that sample will be in supernovae, another 21% or so in AGN, and then some unknown type objects, hostless variables with magnitudes greater than 24, and then classical novae. So, another area of science involves looking for exoplanets. LSST is not going to find Earth-like planets, but it will find a large sample of hot Jupiters, which are large planets that are close by their parent star. So this plot on the left shows, as a function of the planetary period in days and the planetary radius in units of the radius of Jupiter, what is the probability that LSST will find such a system throughout the galaxy. And you can see as we get to large planets with short periods, which means they're close to their parent star, the probability goes to 100%. So that's not terribly surprising, but there still can be a very large population there. And then if you pick a particular value, so a planet with something slightly bigger than Jupiter with a period of 2.8 days, and look at what is the probability of detection as a function of distance, and you can see we would detect such a hot Jupiter out to a few kiloparsecs. So certainly most of our portion of the galaxy we would be sensitive to such activity. Sort of moving out of the Milky Way now to look at the extragalactic sky. LSST will be a unique tool for studies of galaxy formation and galaxy properties. The database will include photometry for something like 10 billion galaxies from the local group out to Z of 6 or so. And for comparison, there are only about 100 billion galaxies in the observable universe. So we will be looking at a sizable fraction of all the galaxies that it is impossible to detect, that it is possible to detect. And we'll have 6-band photometry for a sample of something like 4 billion galaxies. And so lots of things you can do with the data. Key diagnostic tools will include luminosity functions, color luminosity relations, size luminosity relations, quantitative morphological classifications, and of course studies of the dependence of galaxy properties on their environment. So one way of getting a sense of this is by looking at the total co-moving volume which is sampled by LSST. So this is a log scale going up to about 10 to the 12th cubic megaparsecs as a function of redshift. LSST sits roughly here. And you can see it's orders of magnitude higher than essentially all previous surveys that come before it. And of course, opening up that cosmic volume yields a much larger number of objects, but it also allows you to survey further back in time and further rare kinds of systems. The expected sensitivity leads to near complete samples out to high redshifts. So on this left plot, we take a sort of fiducial red sequence galaxy, and its spectrum is shown at a range of different redshifts, as you can see. The LSST points are these purple ones here, where the top of the triangle represents the single visit limiting magnitude, and the bottom of the triangle represents how deep we will get after the 10 years of the survey. And in most of these bands, you can see that we're getting down to redshifts greater than 1, of order a few, which is nicely complementary to the sensitivity of the VISTA survey in the near-infrared and Spitzer and WISE at somewhat longer wavelengths. So that's for a fiducial red sequence galaxy. For alignment break galaxy, you can do similar analysis, and there you see we can get out to redshifts of order 6 or 7. And one thing to emphasize with LSST is it's not just the ability to detect faint galaxies. It's given the large aperture, it's the ability to do low surface brightness imaging of lots of galaxies. And when you do low surface brightness imaging, you discover lots of new features. So this is a case in point where you see a sort of traditional looking spiral, but when you do faint imaging, you see these tidal streams which are tied to the history of the galaxy in the same way we saw earlier for LSST. And here's a good example. This is a galaxy which was imaged by Sloan. So the Sloan image is on the right, and this is the same field imaged with the deep lens survey roughly at LSST depth. And so you can see all the additional information you get about that object when you go to low surface brightness compared to the Sloan image, which would basically just show you a simple isolated elliptical. So again, we'll have data like this on very, very large numbers of galaxies, and one of the challenges will be is how do you automate a system that can characterize these sort of complex morphologies and discover them as, and study them as a function of various other parameters. Okay, moving to AGNs. As you know, AGNs involve massive black holes at the centers of galaxies that release enormous amounts of energy through gravitational infall. In recent years, we've learned that the formation and growth of these central black holes in AGN play a very important role in galaxy evolution through AGN feedback. The enormous dynamic range offered by LSST in luminosity and redshift will revolutionize our understanding of AGN demography and the correlation between AGN properties and their host dark matter halos. So LSST will actually produce a high purity sample of AGNs, roughly greater than 10 million optically selected AGNs. That's at least an order of magnitude larger than the current AGN sample derived from all wavelengths, from the radio to the X-ray. So, you know, you might ask, for faint AGNs where you don't see the host galaxy, how can you tell that it's an active galaxy as opposed to a field star? And you can do that on the basis of the colors, but also the absence of proper motion. So these are color diagrams for the various different color combinations we can construct. The stellar locus is shown as the black points, and where AGNs would sit as a function of their redshift is shown as these color points, as indicated here. And you can see only a relatively small fraction of AGNs actually intersect the stellar locus when you have all these different color combinations to use. But on top of that, in contrast to the stars, remember, we'll be able to detect proper motion of stars out to a kiloparsec or so. The AGNs will not be moving in the sky. And so that gives you another criterion. But finally, the final thing which yields very high purity samples is the intrinsic variability, because essentially all AGNs are variable. And that's kind of illustrated here, where as a function of absolute magnitude and redshift, we plot the probability that we would unambiguously identify an object as an AGN. And the color scale of probability is shown here. Now, if you only have a few visits, you get the plot on the left, and you can see you're still kind of telling that most objects are AGNs, but as you get down to fainter magnitudes and higher redshifts, it becomes a little bit more unclear. On the other hand, if you have the full sample of many, many visits and exposures, as we have on the right, then essentially we have unit probability for unambiguously detecting the system. Okay, let me turn to supernovae. Roughly 1,000 supernovae have been discovered throughout the history of all of astronomy. LSST will find something like 10 million over its 10-year duration, spanning a broad redshift range with precise uniform calibration. That will undoubtedly revolutionize the field, allowing large samples for studies of systematic effects and additional parametric dependencies. We'll have something like 100,000 supernovae in what we call deep drilling fields, which will have very well-measured light curves in all 6 colors. And of course, that's an excellent sample for precision cosmology. And interestingly, the large sample size will allow us for the first time to conduct Hubble diagrams for type 1a supernovae as a function of direction in the sky. Rather than looking at the whole sky, we can choose narrow ranges of sky and still get enough statistics to do the Hubble diagram. And that'll give us stringent tests of the fundamental cosmological assumptions of the homogeneity and isotropy of the universe. And of course, we're not expecting departures from homogeneity and isotropy, but it's interesting to do the check. So these are some sample Lightcurve simulations. In the main survey, where we just catch supernovae as we're scanning over fields, we'll unambiguously identify objects as supernovae, but our light curves won't be that great. So what you're looking at here, the green lines show the theoretical light curves, and the little black points that you can sort of make out there would be our observations. And as you can see, the sampling in the main survey is great. But in the deep drilling fields, which, as I said, will still have of order 100,000 over the 10 years, there you can see the sampling is extremely good in all of the colors. And that will allow us to drive very good light curves and probably photometric redshifts from the supernova light curves themselves. Of course, we can also use the host galaxies to get redshifts. So we'll have a large sample of supernovae. We won't do follow-up spectroscopy of anything but a fraction of these, but we believe we'll get good enough redshift information from the photometry alone and very good estimates of the absolute magnitude based on light curves. Strong gravitational lensing. LSST will provide time-dependent imaging of an unprecedented sample of strong gravitational lensing events. And this is especially important for rare classes of events like lens supernovae, which we'll probably see for the first time, which are crucial for cosmography. These data are interesting because they can provide information on the substructure and dark matter distributions of galaxies that is difficult to derive by any other means. And strong lensing will also enable us to do micro-imaging of distant sources, which could enable the study of accretion destruction of distant AGNs. So these are what strong lenses will look like. You can see the multiple images. You can pick them out on the basis of their colors in relation to the lensing galaxy itself and also the morphology. This next slide tells you what sort of the numbers are. So these are the numbers of strong lenses as a function of their magnitude for various different classes, for double lenses, quads, and cusps, etc. And compared to Sloan, you can see that LSST will increase the sample by roughly 2 orders of magnitude. So we'll change with what is somewhat a niche field due to limiting statistics into a very rich field where we have large samples. And on the right, we're showing here what the redshift distribution of the lensing galaxies is and of the background AGNs or quasars that will be used to, that will be strongly lensed by the foreground galaxies. An interesting case is these lens supernovae that I mentioned earlier. So on the left here, we're showing the number of supernovae as a function of redshift for LSST, both the type 1As in the solid line and all supernovae in the dashed line. Now, the probability that a supernova actually lies directly behind a foreground lensing object like a group of galaxies or a cluster of galaxies is pretty low. It's something like a part in 10 to the 5 or so. But when you have such a large sample of supernovae, then you end up with non-negligible samples of lens supernovae. So we'll see hundreds of objects like this. And of course, these are quite interesting because we know what the light curve should be, and so we can time the dependencies of the various different multiple images in the strong lens to actually derive really interesting information for cosmography and for the substructure of the dark matter halo. And on the plot on the right just shows what the distribution as a function of type of these lens supernovae will look like. So let me close with a brief discussion of dark energy. many of you are involved with the dark energy survey that's currently in operation. LSST will probe the nature of dark energy via a distinct set of complementary probes using type 1a supernovae as standard candles, measuring baryon acoustic oscillations as standard rulers, studies of the growth of structure via weak gravitational lensing, and also the growth of structure via the statistics of clusters of galaxies. So in conjunction with one another, this rich spectrum of tests is crucial for reduction of systematics and dependence on nuisance parameters. And these tests also provide interesting constraints on other topics in fundamental physics, like the nature of inflation, modifications to general relativity, and the masses of neutrinos. These are the LSST predictions for galaxy auto and cross power spectra. So these are just using the positions and redshifts of galaxies to determine the mass power spectrum. And the baryon acoustic oscillations, which many of you are familiar with, are these subtle ripples that you see on these curves. The gray envelope sort of gives our statistical error, which is limited on the largest angular scales by just cosmic variance. And on the smaller scales, it gets very small because we have so many galaxies. And you can see that the BAO features should be detected by LSST at a wide range of redshifts at very high significance. This plot shows the weak lensing power spectrum, which will be determined by measuring the shapes of all of these galaxies as a function of multipole moment for different tomographic redshift bands. So we'll do these weak lensing correlation studies for galaxies within given redshift bands as determined photometrically. And again, the error bars here show the precision that LSST will get. At the small angular scales, it's limited by the number of galaxies. On the large angular scales, it's limited by cosmic variance. And just for comparison, this shows you what the predictions would be for a dark energy model with the equation of state parameter of -0.9 instead of -1. And you can see that's easily discernible. So LSST with weak lensing alone has the capability of determining W to of order of percent or so. And in fact, this is a summary of, when you put all those techniques together, what the constraints on W today are versus its derivative with respect to the expansion factor. The important point to make about this plot is you get lots of different contours from different techniques. If you put all of them together, then you get this yellow region, which is smaller than just the overlap of the contours. And the reason for that is that these different techniques are sensitive to different systematics and different cosmological nuisance parameters. And so the full suite of observations is much more powerful than just coupling any, than looking at any one of them together. So LSST has the power to, with the highest precision that anybody's really talking about now, of actually determining the cosmological parameters. But what I personally think will be more important is checking the consistency of the cosmological model against all of these different sorts of measurements. Okay, in my last few minutes, let me just talk a little bit about how we're preparing to do this survey. And we've taken an approach which is much more characteristic of high energy physics than it is of astronomy, which is to do very extensive simulations of the behavior of the entire system. So, and the new philosophy of survey development is through high fidelity simulations. And that involves simulating the sky itself by producing cosmological catalogs as well as catalogs of solar system object transients, etc. And then doing a very high fidelity tracing of what the light from those individual objects in the catalog will do as it passes through the atmosphere on into the optics and the camera of our system. And we do that photon by photon, which is a very new approach for optical astronomy. And then finally, you produce these simulated images, and you can then analyze them using your data management or your data analysis techniques. And you can compare what you derive from the data against what you know you put into the data to actually calibrate and understand the systematics that have to do not only with the hardware but with the software modules that you incorporate in producing the data. So this shows what our photon simulator is generating. So we trace every photon through multiple layers of a turbulent atmosphere with screens that give a good representation of the Kolmogorov turbulence that you see in the sky. And then every one of those photons comes down, reflects off each of the optical surfaces through the refractive lenses on into the camera, where you get charge conversion and the ultimate, then we track the actual photoelectron down to the detector. And when you go to that sort of detail, you can really investigate the effects of subtle engineering features of the system. So that's kind of illustrated here. And notice there's a series of plots here, and the angular scale is changing as we go from the top left to the bottom right. So at the top left, 0.2 arc seconds corresponds to that broad white beam that you see, and down at the bottom, it's more like this in size. So these are the contributions to the image profile just due to the intrinsic aberrations in the optical system. It has an interesting pattern there where you can see it's much smaller than the size of an individual pixel, which is 0.2 arc seconds. If you turn on tracking errors, then you get a little bit of a distortion here, diffraction due to the spider, etc. Detector perturbations due to misalignments at the tolerances levels we've adopted, perturbs this a bit. Lens perturbations, figure errors in the mirrors, then charge spreading in the detector has a big effect. Dome seeing creates some correlated distributions. And then finally, when you put in the atmosphere, so the low altitude atmosphere, which looks like dome seeing, mid altitude atmosphere, and the high altitude atmosphere, which gives you a much more rounded looking image. And then finally, the pixelization that occurs with 0.2 arc second pixels. And so you can turn on each of these different effects and actually see the result through the end scientific analysis. We can make complete simulated images with any of these effects turned on or off, and then carry out our analyses and see what differences come. So it's a very powerful tool for understanding systematics. This is an image of a single CCD taken in 3 different colors. So this false color here is an indication of the intrinsic color of the objects. And you can see how realistic these simulations look like. We get the traditional spiders, some bleeding in the CCDs, the various different morphologies of different objects. If you blow up a piece of that image, you can see what stars look like, what elliptical galaxies look like, what some of the spirals look like, etc. These are 3 different segments of one CCD sensor for one 15-second exposure. Again, you can see the kind of faint objects that we see and how we can do all these studies. And here's an example where you see the diffraction and, from the spider and the bleeding in the CCD itself of a bright star. If you simulate the entire focal plane, you get a picture like this where now you can see all the sensors. You can't see very many stars or galaxies just because of the resolution of my computer screen or your projector. You know, they're much too small. You can see the bright objects. Most of what you're seeing here is the tapestry associated with the subtle electronic biases and gain variations for the different readout segments of the CCDs. So a single simulation of one 15-second exposure is 3 billion pixels covering 10 square degrees. There are 20 million sources detected in that 15-second exposure. 10 billion photons, takes 11 gigabytes to store it, and this single 15-second image takes 1,000 CPU hours to compute. But of course, we can do these on highly parallelized facilities and generate complete simulations. So scientifically, one of the things we've been doing that is looking at what will be among the most sensitive measurements made with LSST, which will involve weak gravitational lensing. And there you worry about what are the ellipticity contributions that are introduced by the atmosphere using a ground-based telescope. So this shows real data of ellipticity with its sign in one of its 2 components as a function of position in the field. You can see this streaking in the data, which is actually associated with the passage of turbulent structures in the atmosphere due to the wind in one particular direction. And that leads a preferred correlation in one direction versus the cross direction. And when we simulate this just, ab initio without trying to adjust anything to match the data, we get very similar images from our simulations. So we have pretty high confidence that we're simulating the atmospheric effects properly. As I mentioned, you can turn things on and off. So if you have no misalignments of any elements of the system, then this is the ellipticity distribution of the focal plane that we would get. when you put in the various different detector misalignments that we're speccing to and the lens misalignments, you get a more interesting pattern. But you know that, notice that still these ellipticities are really relatively small. But anyway, this is a way of validating that the engineering requirements we've adopted for the system are appropriate. So let me conclude now, just sort of at the end of my time. LSST science opportunities are extremely rich, ranging from studies of the smallest objects in the solar system to the structure and dynamics of the universe as a whole. Most of these investigations can be performed using data from a single coherent survey program, so that's what we call massively parallel astrophysics. The analyses are complex and they require significant attention to detailed systematics uncertainties. Basically, in order to use the very high statistics for any kind of science investigation that LSST will produce, then you need to sort of understand your systematics at a comparable level of precision. So there are many opportunities for scientists to become involved now in helping us to optimize the anticipated science that will come from this marvelous facility. And so we're very hopeful that there will be Brazilian engagement in this project and lots of areas where many of you can help us to study these effects. Okay, let me close there. Thank you very much.
Okay, thank you.